All right, so we're on to our last Earth science lesson of the year, and we're going to wrap up our study of plate tectonics. You'll remember that last week we talked about Wegener and his continental drift theory, and I mentioned that parts of that theory were commonly accepted today as how it is that continents can move over time. And the modern name that that theory goes by is plate tectonics. So by the end of this lesson, you are going to be able to explain how our current understanding is that continents move. So, plate tectonic theory. Here's what it's all about. Remember that the Earth isn't the same all the way through. It's broken up into layers. And depending on what we're talking about, those layers have different names. If we're referring to them just by what they're made up of or their composition, that would be the stuff on the left over there, the compositional layers, where you have solid crust on the outside, liquid mantle, then two layers of core. If we're referring to them based on how they act and what they do, those are the mechanical layers. And essentially, what happens there is the mantle gets broken up a little bit more and the core gets broken up a little bit. So with the mechanical layers, we define the outer and inner core because those do different things. Like the outer core is liquid, the inner core is solid. And it turns out that not all of the mantle is liquid. So we break the mantle down into parts that are solid, parts that are kind of starting to liquefy, and parts that are liquid. So in the mechanical layers, that outermost solid layer we call the lithosphere. And then the next layer down we call the asthenosphere. Now, these names make sense if you look at the meanings of those prefixes. The prefix litho means rock. So the lithosphere, that's the rock layer. The asthenosphere, and you'll note in the picture, it has the British spelling of the word with the AE. In American, we spell it without the E. So go wild, pick the spelling you like best, I guess. But whichever way you spell it, astheno means weak. So that's the part where it's still solid, but it's a higher temperature. So it's a little closer to fluid. So it's a solid, but it's much more movable. So then below that, you've got the true liquid in the mesosphere. It's this layering that causes the whole thing to work. And it's this layering that Wegener didn't know about. So he could never really figure out how it was that his idea worked because he was missing this critical piece of information. Down. The lithosphere, that solid rocky part, is divided up into segments. It's not one solid mass. We call these segments plates. These plates are movable, and they're movable because they're sitting on top of the more mobile asthenosphere that can get pushed around by convection currents in the mantle. We, I believe, have talked about convection currents before, but just to refresh your memory, as things get hotter, the molecules within them get more energy. So they move around more, they spread out from each other. So the hotter a substance gets, the less dense it gets. Density is just a matter of how many molecules there are in a unit of space. So the more the molecules are moving around and spreading out, the less dense the material is. And things that are less dense tend to rise. So in the mantle, what you see happening is the bottommost part of the mantle, the part nearest to the core, is the hottest. So the liquid rock that is down there closest to the core heats up. As it heats up, it gets less dense, so it rises towards the top layers of the mantle. There, because it's farther away from the heat of the core and the pressure of the core, it starts to cool down. And as it cools, the molecules now have less energy, so they tend to get closer together. So the liquid rock gets more dense, so it sinks. And this rising and sinking goes in a circular kind of pattern that as it comes up to the top, it could push the plate above it a little bit this way, or if it's going that way, it could push the plate a little bit that way. And kind of the problem with this is the plates don't have very far to go. Like, the crust isn't solid, but it goes all the way around the Earth. So eventually, if these plates are moving, they're going to start moving up against each other and interacting with each other. We talk about these edges where the plates line up. We call these boundaries, plate boundaries. And we have three types of them: convergent, divergent, and transform. We're going to talk about what those three are. So, to converge means to move towards each other. So whenever two plates are going towards each other, we call that a convergent plate boundary. And when that happens, we've got two solid masses. They can't just move through each other. So one of them is going to get pushed under the other one, kind of like this. And what you see happening with my hands is the same thing that's going to happen with the plate boundary. On the one edge, the edge that gets pushed under, you're going to tend to see kind of a rift or a valley form. And on the other edge, the edge that's coming up over the top, you're going to tend to see a mountain range form. Now, which plate does what? Well, that depends on what two kinds of plate are running into each other. So convergent plate boundaries are the trickiest of the three types because what they're going to do depends on what kind of plates you've got. If it's two plates that have ocean on top of them, flip a coin. One plate is going to get pushed under the other, but they're roughly the same thickness, roughly the same density, so it could be either one. On the downward side, you're going to get some kind of a trench, and on the upward side, you're going to get seafloor volcanoes. And these volcanoes, if they get big enough, can form volcanic islands. Think the Aleutian Islands in Alaska. Think Guam or Tonga. Hawaii is also a volcanic island chain, but not because of this. We're going to talk about Hawaii in a little bit, so stay tuned. The same kind of coin toss happens with two continental plates. Again, they're about the same density, they're about the same thickness, so 50-50 chance. One plate's going to get pushed under, one plate's going to come up over the top. On the side that comes up over the top, you will tend to see mountain ranges forming. For example, the Himalayas were formed by this kind of continent-continent collision. Now, ocean continent, that one is much more predictable. If an ocean plate runs into a continent plate, the continent plate will win every time. It'll come out on the top because ocean plates are denser. So they will always end up getting pushed under. So what you'll see is a trench that forms on the ocean side and volcanic mountain range that forms on the continent side. Think the Andes in South America, the Cascades or the Sierra Nevada. All of those would be examples of a collision between ocean and continent plates. Divergent plate boundaries, they're a lot easier because the same thing is going to happen no matter what. Diverge means to move away from each other. So when two plates are headed in opposite directions, we call the boundary between them a divergent boundary. And what's going to happen there is, well, all of a sudden you've got a hole in the crust. And what's underneath the crust? Magma, lava. So that's going to bubble up. It's going to hit whatever's up above either water or air, depending on whether this is happening. And it's going to cool and solidify and form new land. So divergent plate boundaries are where new land is formed. And we have different names for this depending on where it's happening. If it's happening underwater, we call the result, you have an oceanic ridge where the edges of the plates are with a trench down the middle. For example, the Mid-Atlantic Ridge, the Atlantic Ocean is currently getting bigger. So right down it, there is the Mid-Atlantic Ridge where the two plates that meet in the Atlantic Ocean are pulling apart. So you've got ridge, new land being formed in the middle. If this is happening on land, the same kind of a deal happens. We just give it a different name. We call it a rift valley. So, for example, this is happening in Eastern Africa. Very creatively, we have named that landform the East African Rift Valley. Not our finest moment as geologists, but what you gonna do? Now, transform boundaries are the fun ones because sometimes the plates aren't coming together or going apart. They're just kind of sliding past each other. One's going forward, one's going back. And we call the space between those two plates a fault. Along faults, or you'll hear them called fault lines, the plates are grinding against each other because just because they're moving does not mean that there aren't all kinds of little edges that could catch on one another. So this isn't a very smooth process, this transform movement, which means one hallmark of transform boundaries, besides that fault line, is along these boundaries, you will get many, many earthquakes. So, for example, in California, we have the San Andreas Fault, where two plates are sliding along each other, which is why California has as many earthquakes as it has. Now, I promised we'd talk about Hawaii, and this is the moment that we get back to it. Because Hawaii, you'll find when you get into this week's work, and I give you a map of where all of these plate boundaries are, Hawaii is kind of out in the middle of the Pacific plate. It's not near any plate boundary at all, but if you listen to the news, you know that there are volcanoes in Hawaii and they frequently erupt. So, how can that be when they're not close to a plate boundary where we'd expect that to happen? Well, the mantle is not perfectly uniform. There are areas within the mantle that are warmer than other areas. We call these hotspots. And the land above a hotspot, it'll tend to kind of melt the rock that's up above it just because it's so much hotter there than the typical temperature of the mantle. So when you get that hotspot that forms, you get volcanoes out in the middle of nothing. So the Hawaiian Islands have formed as the hotspot is here, and the Pacific plate very slowly moves over top of it. So every time it moves on a little ways, a new volcano forms. And in fact, a new volcanic island is forming in Hawaii right now. We're still a very, very, very long way from it breaking surface. Offhand, I don't think it's going to happen in your lifetime or my lifetime, but it is happening right now that new island is forming in Hawaii. So, how did we work all of this out? Well, we've been able to pretty accurately map out where the edges of plates are based on those kinds of geological features that I was telling you about. So, by plotting out the kinds of geological features we see, we can figure out not only where are the plate boundaries, but what direction those plates are moving. So you're going to do a little bit of that for your work this week. Just to remind you, this is our last week of classes before CAP. So I am giving you from right now until the end of CAP week, which is next Thursday, to complete this last set of assignments. Go do good work. Be good, be safe, be kind. Don't do anything I wouldn't do. And enjoy your new discoveries.